Hi there, everybody. Sorry we had an interruption because we had an exam yesterday and a whole day has gone by, including that we now have a different president from the last time we were together. So, welcome. Um, welcome back. So just to pick up where we were on this, we were talking about work and PV work using pistons. So when we have the expansion and PV work, in this case, we are going to have delta, oops, I should probably switch back to the normal pen color. Delta V is greater than 0. Okay, and this means you had an expansion, right? And that means that work is less than 0. In other words, this is an expansion, right? Because we went from the gas being like this, and the gas expanded. That's what this is showing over here. And the work is negative because the system that is the gas inside the piston is doing work on surroundings. In other words, this pressure or the weight is the external surroundings. And the gas, when it was heated, went from like this volume to the larger volume. And we have the dotted line here to indicate that that was the original position. So there was a change in height in the piston, which is some delta H, which corresponds to some delta V, so that it has gone up. So now we have work, which we just said was negative. So I'm just going to put a little negative sign on top of that, equals negative P delta V. What this does not mean is to plug an extra negative sign in. It means that the work we expect will have a negative sign from this inequality right up here. This means work is more negative because it just had to push up for the delta V. Before the expansion, what was the situation? The P of the system was greater than the pressure of surroundings. Right, and the reason is because it had gotten heated after the expansion. So what will happen, right? P external will be equal to the P final, right? So in other words, the buildup of the pressure as a result of heating the gas is what caused the gas to expand. So it would be like you had a piston and you put it on top of a candle, some fire of some kind. And at the instant after it's been heated, but that the piston is in the original position. So this, of course, is a bit of a contrived thing because the piston would be moving as you're heating it, right? But imagine you could, like, I don't know, lock it in place, I guess. You would say at the instant after you've finished heating it, but before the gas has done an expansion, that's what our initial state is like. And then that gas does the work to push this weighted external pressure, represented as some kind of a weight or a box on top. It expands. And when is it going to stop expanding? Well, when it doesn't have the advantage of having more pressure, right? So when the pressure internal is equal to the pressure external, that's when the piston stops moving. And that's basically what we're just writing down here. And hopefully that all makes intuitive sense. In other words, i.e., the pressure equalizes. All right. Now we have the opposite situation. So it could expand, but there also could be a contraction. And PV work. Okay, so the opposite situation is gonna happen. So we can sketch a beaker. I mean, a piston. Sorry, the picture that I actually draw is kind of similar. All right, so we're gonna have a piston kind of up near the top. All right, there's the piston in there, and it's got a weighted box. I'm not drawing it maybe in all the lovely detail, but I think you get the idea. Okay, there's the weight on the top, and here's the piston, and it's got some depth. Gas is getting through, right? And there's some gas in here. Gas, and the gas is kind of diffuse right now. Jeez, I think I actually did like 12 dots. All right. Okay, and then what's gonna happen? I guess so we're gonna have some P external, right? We'll be doing something and there will be an event happening. Contraction of the gas. All right. And then what's gonna be the result? It would be nice if we could have these both on the screen simultaneously. Something like this. It's a piston, and here's that. And now the piston is lower. Dun, dun, dun. All right. It's very low. All right, and the weight is the same size. Yes, it's gonna make it believable that's the same box. All right. The box did not change size despite what the picture may look like. All right. And so this was the initial position, right? And so what's happened is we've had a change in the height of the piston. Yeah, this is height initial, and this is the height final. And we have some delta H running along here. You could even do it like this to highlight that, right? Delta H. There we go. All right. And what has happened here? Piston moves down. The gas contracts. Surroundings do work. On the system. All right, and we should probably put some gas in here. Now, that was a pretty diffuse gas, but now it's gonna be a lot more dense because it's squished together. And there's vacuum in between. It's probably not the same number of dots, but you get the idea of what I'm trying to show here. All right, it's trying to give some proxy for the pressure here. All right, so now we need to just keep our notes here about what's going on. So delta V is less than 0, and therefore work is greater than 0. The work now is gonna have a positive sign equals negative P delta V, which we now expect has a negative sign because the volume was got squished. So If the volume is negative, then the work becomes positive because, right, of the negative times the negative, this negative comes in the formula, this negative comes from the value that is plugged in. So before the expansion, pressure of the system is less than the pressure of the surroundings. After the expansion, pressure external equals the pressure final. All right, so it's more or less the opposite. Okay, now that's great. Hopefully now we have an intuitive feel for what is going on in the pistons. But we need to now have some tools to calculate this in a bit of a more detailed way. So work as an integral. Thought you were gonna get away from calculus. If the external is not constant, then the work must be that does not look readable, must be evaluated as an integral. Why? Well, the reason is because if something's not constant, we're going to have to take the area under the curve, see what that's going to be. So it's going to be something like this. Work equals VI to VF B external. And notice that if the pressure were constant, you still could solve it with the integral, but it's gonna simplify to just a rectangle, right? Which is why you can just do the simple formulas that we wrote down. So this, in other words, is the pressure external as a function of the volume. That's what this says, right? That's this term right here. So the equation for P external would need to be provided so that the integral could be calculated, right? You can't just like know that. So you have to have something like that. Otherwise, you wouldn't be able to calculate what it is. And this could model a mechanical device or like like a piston that's driven piston, right? Because this never made sense to me when I was studying thermodynamics, because I was always thinking, well, how does the atmospheric pressure actually get all that much different? But the point is that it's not necessarily the atmospheric pressure that we're talking about, it's that weight that we put on top. So if you think about it in terms of that box that we had on top of the piston here, you might imagine that this is actually a piston being driven by some kind of a mechanical device, or it might be representing something else. And this would make a lot of sense in terms of like manufacturing or machines and that kind of thing, where you would in fact have a piston attached to something. Or you think about your car, for example. In a vehicle, the piston in the engine of the car is going to be driven forward by the burning of some kind of a fossil fuel if you drive that sort of vehicle. And the expansion of the piston then is what drives drives the vehicle to drive, right? So that's how a combustion engine works. It's the same thing in locomotives and many other kinds of mechanical devices. And of course, at the time when a lot of this was working out, the West was now won, and we were driving forward into the great territories of the United States and building railroads and building trains to go out there. And so that's why a lot of this stuff was very important for the development of the history of the US, whether you agree with the expansion or not. Anyways, that's the thermodynamics point of view, what happened. The difference between integration and negative P delta, yeah, that's not quite right. Negative. Right, so what we want to consider is, how do you know which one to use? Do you need to do the integration, or can you just use the easy formula? Here's a graphical approach for those who might understand this sort of thing better. All right, so graphical approach, we need a graph. All right, P. In other words, this is understood to be the external pressure. And here we're going to have some volume 1 and we're going to have some volume 2. And this axis is the volume. All right. And then we're going to have some kind of a curve. All right. So we're going to go. Great. Okay. And so the important thing about this curve is that it is not flat, right, on the top, right? It's got some curvature. Hence the term that it is. Okay. Oh, this is quite helpful to have these grid marks. Okay. So now let's see what we would do. Yeah, this is exactly the point we want to make. Now we need this. All right, I'm drawing some nice little picture here. All right, and then we need, oh, the highlighter would be perfect. All right. And again, this is probably not going to be a perfect sketch, but it is a sketch. You can get the idea of what I am doing here, and that I am blurring the area under the curve. All right. Now, let's consider what's going on here. These tools are actually pretty good for this. All right, nice figure. I have two things here. All right, so we're gonna need to make some little notes on the side about these things. It's gonna be some colors over here. And put a little key over here for our graph. All right, so I just colored in a rectangle in two different ways. So let's see what we got. Okay, this one is the integral work. And this one is the negative P delta V work. Okay, so we should all be familiar with the idea that taking the integral is really just taking the area under the curve, and it's like the Riemann sums where you basically have rectangles and you take the area of the individual rectangles and the limit as um, as you make more and more rectangles to fit in the space, it will get increasingly accurate. Hopefully you'll remember these ideas from calculus. And so we see that the integral work is a much smaller area than the P delta V work because there's this piece up here that's sort of triangular shaped that's not filled in, right? That's the key thing here. And so the integral work is going to be much more precise. I mean, the P delta V work is like a Riemann sum in the opposite of the correct limit because you only have one rectangle instead of having lots of little rectangles, whereas the integral is really going to be computed by a whole bunch of smaller rectangles. And so that is a graphical illustration of the differences of computing the work using the integral, where we would get the orange value, whereas the negative P delta V work would be a much more crude way of doing this, which would get you the work by doing volume initial and final. And see how this part up here, right, is representative of the pressure. And so we said we could use the negative P delta V work when the external pressure is constant. And you see that P external is basically the value in the y-axis, and it is constant in this situation. So if your curve is actually a straight line, because this is y-axis is representing the pressure external, that it totally makes sense to just do negative P delta V, right? I mean, why make life difficult? And so you would get that value from there, and that would be a straight line. But anyways, yeah, that's a graphical representation, which I hope helps you see it. But let's capture some of those thoughts in some notes over here. So the rectangle P delta V for constant is the negative constant P external, right? If the pressure is changing, you take the area under the isotherm. Curve using the integral. Okay. We also have another note we need to put on this graph. This is the isotherm. What does iso mean? Iso means it stays the same. Okay, iso itself stays the same, kind of like eigen, except it's iso. Similar meaning. Okay, isotherm means that it is at constant temperature. Right, so if the temperature starts changing, we need to have a 3D graph and not a 2D graph. Right now, we're going to keep it simple and say the temperature stays the same, which of course isn't realistic because you cannot exactly enforce that in real life, but approximately. Okay, integrating under the isotherm represents the minimum work that could be expended to achieve delta V. Just notice that that one is smaller than the blue hatched area, right? Integrating under the isotherm represents minimum work that could be expended to achieve delta V. Yeah. Notice work is not a state function. We'll have more to say about state functions, but basically state functions have this property that the path that you take to do it is not important. And if you have taken some advanced math classes, you may have encountered path dependent versus path independent integrals, and this totally is coming into play. Okay, state functions we'll have more to say about. More work could be expended more work than just doing the simple one, because if the external pressure is such that P external greater than P internal, a compression will result. That is, any P external greater than P internal it's an imbalance, right? It's gonna move. Will cause a compression. All else being equal, of course. The minimum P external get a compression is infinitesimally greater. Sure, I spelled that right. INFINTESSANALI greater than then results in walking along the isotherm. Minimum. This is called reversible isothermal compression. Reversible means P external approximately equal to P internal, and P external is infinite. P internal. All right. What exactly does this mean? All right, so let's just take a look at this curve and think about pistons. So if you are going to do a compression, right? So we're thinking about compression, that's this process here. Go from here to there, right? So how is it going to happen? Well, it happens if the external pressure is greater than the internal pressure, with all else being equal, meaning temperature, for example, because we're talking about along an isotherm, right? So that means temperature is the same. So how could you make the piston go down? Well, I mean, you could put a heavier box on top, right? So yeah, so the idea is you're capturing the system in the instant before something happens, and you put a weight on it and it goes down, right? So these pictures always are like kind of a little bit misleading because they don't really show the time of the event. So it's like the instant before this picture here, there would be like no, like the external pressure would be equal to the internal pressure. And then you put a heavy box on top. Okay, and at that instant, before the pistons start moving, is our initial condition. Okay, and then it's going to push the piston down and squish the gas. Great. So that would be if you're going to do it all in one fell swoop. But suppose instead, okay, so that all in one fell swoop is pretty representative of this kind of P delta V work, which you get from the blue hatched area. But what if you were going to do this in the infinitesimal way? All right, so that would be like if you had this compression, but instead of putting the big box on top, like the minimum amount of work you could do is you could push it like a little teeny bit, right? And then you could add it. So you instead of moving it down in one fell swoop, you would just kind of like put a little teeny bit on each time and like make it move. So if you put, instead of putting a whole box, maybe you put like, I don't know, maybe you open the box up and it's got, I don't know, paper clips in it. Okay, and instead of putting the whole box of paper clips on, you just put one paper clip at a time. And you just walk down so that the piston went down like just a teeny tiny bit. And then you said, okay, oh, it's not there yet. Let's put a few more. And you put some more paper clips on and you pushed it down and it went down very slowly. Okay. That is what happens when you do it this way. So you mean the amount of work is not the same? That's exactly what I'm saying. The amount of work is not the same. Okay. Work is not a state function. And what we mean by it not being a state function is it depends how you do it. Um, I walk over to the science building where I work, and I have the choice to either walk up the hill, up Foss Hill, and go up by the observatory and come back down over the hill, or there's a path that's been worn on the side of the hill that's more or less level. And so it's always a question of which way am I gonna walk over to my office? So I start at the same place and I end at the same place. So I start before Foss Hill and then I get over to the Hall Atwater and I'll enter it Exley building by traversing this hill. And so the amount of work that I personally do is not the same, although from going from one point to the other, it's exactly the same. And so it's a lot harder to walk over the top of the hill, and it's much more obvious as well. If you don't believe that, is try doing it jogging. So sometimes I also use that route in my exercise, and it is not the same to go over and down the hill as it is to walk on the side, although my initial and final location may be the same. That's what we mean by state function. Guess what? And that is our next topic. So state functions. Hopefully that analogy helps you to see, but what we're saying is that work is not a state function. Yeah, a state is known when all the variables to describe the system completely have known values. Sometimes in my research, we use phase space. Example, 1 mole of gas. Is defined completely variables of state. Variables that tell the state of it: the pressure, the molar volume, and the temperature, which is why these are the things that are in the ideal gas equation. And but because the relationship of these things is known to each other, right? If you're missing one of them, you can go and calculate another one. So any two actually is enough, because you could always calculate the third one, because you know how to do algebra. State function depends only on the state of the system. A path-dependent function, however, depends on the system, how the system got there. Like, does it matter which way I walk to work? Or if I were ambitious and jogged to work, I would probably be feeling it if I ran over the hill to get there, versus if I took the easy way. We say it's half-ended. Independence are state functions so the ones that do not depend, they're called state functions and are designated by the capital letters. And they use delta instead of whereas. Dependent have the lowercase letters. Wow, it's like programming. Case matters in thermodynamics. And use this. Okay, so what we mean here is this is capital delta. This is initial, means initial minus final. Okay, and this is for infinitesimal. Infinitesimal, yeah, I should use the delta. Infinitesimal changes as you go along. So we've just seen an example. Okay, this one is big delta, and this one is the little delta. Okay, this one is path independent, and this is path dependent, right? So that's an example of those different things. Okay. Example. Energy is path independent. In other words, we could also say it's a state function. And can be expressed as delta instead of the actual integral. How convenient. Being able to use the big delta always means the math is easier. In other words, internal energy right? Easy function, easy formula. You can just use this. You don't need to do the whole thing. Another example, work, which has a little w, and heat are path dependent. So, for example, we just saw work expressed as an integral above. So this means you might go from some state 1 to 2, dw equals work. In other words, work is not equal to W2 minus W1. And now we could also have the same thing about heat. So Q is for heat equals Q. Heat is not equal to Q2 minus Q1. In other words, these are path functions. That can be expressed as a function of pressure. Calculate the pressure of a system. PV equals nRT instantaneously. Solve for the pressure as you compress the gas. Remember, we're doing this stepwise instead of in one fell swoop. So you would need to do it a little bit at a time, right? So the pressure would change. So what you need to do is you need to recompute many times. So it would be something like this. Work reversible. So the reversible means we're doing that infinitesimal thing. Okay, negative V1 to V2. Here's the pressure of the gas, dV. We apply PV equals nRT. Then we can solve for this P equals nRT over V. Yeah, that's where that comes from. All right, equals negative V1 to V2 of nRT over V dV, right? Because I need this to be as a function of V. Okay, so there's our variable. In other words, I could actually write this as P as a function of V equals nRT T times 1 over V, where these are the constants. They're being held constant in the problem, and here's the variable, right? So this is like y of x, and this is like the x, okay? That's more or less what we're, constant times x is what we're saying here. So we rewrote it, and hopefully looking at it like from a math point of view, it kind of makes sense. So there's our variable. I often thought we should have a class like thermodynamics for the mathematically inclined. I should write the book. So then we're going to factor out the constants. So n RT integral of v1 to v2 of 1 over v dv. This was factor out the constants. Okay, this was given. This one was right as a function p of v. Okay, factor out the constants. Next, we need to solve the integral. All right, so that's going to be equal to negative nRT ln v evaluated on v1 to v2. Remember, that's the evaluation point, right? So what happened here? You need to recall a math fact. Recall that the integral of 1 over x dx equals ln x. That's where that thing came from, right? So this is just a constant times the integral of 1 over x. Is just the variable is called v here, dv, right, with respect to v, and that's ln of x. Great. So that's solve the integral. Okay, and now we're going to substitute in the values. So that equals negative nRT ln v2 minus negative nRT ln v1. Okay, and in other words, this is the upper minus lower. Remember, you have your upper bound and you have your lower bound. This is calculus stuff that hopefully is ringing a bell here. Okay, and so now we're going to remember our rules from laws of logarithms. All right, so this was sub and bounds. And laws of logarithms say that if you have the subtraction of something, you can actually move it into the you can do it as the division. Okay, equals negative nRT ln v2 over v1. This is factoring in laws of logs. Oh yeah, I guess I don't really need to do that factoring. Right, and that's what happened there. Yeah, recall. Yeah, let's just put this here. Recall the laws of logarithms. Ln x ln y equals ln of x over y. All right. Laws of logs is where that came from. All right. So then this brings us to the first law of thermodynamics. We have a lot. Right. First law of thermodynamics. kind of an important topic. Energy is a state function. So energy as a state function depends on the two path dependent functions. Heat and work. Heat, which has the letter Q, and work as the letter W. Why doesn't he have H? Because it kind of looks like Plonk, and they finally realized there's more letters in the alphabet, and I don't know. All right, so du equals dq plus dw. Delta u q plus w. This is the differential form. And this is the integrated form. And this here is the first law of thermodynamics. Kind of important stuff. But okay, yes, by the way, just in case you haven't picked up on this, the U is the energy we're talking about. This one is heat, and this one is work. Choice of letters, not always the best phonetic choice. However, it is consistent historically. So we're gonna go with that. Okay. First law is the law of conservation of energy. Total energy is conserved. And hopefully that intuitively makes sense to you. And why did this all of a sudden have such a giant? Okay, so hopefully that makes sense to you. Even though Q and W are path dependent, oops, not deep dependent. The sum gives a path dependent value for energy. Okay, so that means that somehow these path dependent things have to compensate for each other, right? And that's essentially exactly what these equations right here are telling us. It says that the total energy is equal to the sum of the two parts. This is actually a really important equation, so I think I'm gonna go ahead and just highlight this for our future reference, just to remind ourselves that, yeah, this one is important in case first law of thermodynamics didn't clue you in on that. This one is very important, okay? So you want to make sure you know this one. Yeah, very important. Very important. All right. The two things compensate for each other. That's really what this is saying. All right, I think we're gonna leave it at this place here for today. So next time we're gonna get into the adiabatic processes and talk about some more exciting things about various paths. So we've just been mentioning about the path dependence and path independence of various situations going on here. Um, so let's just do a quick summary of where we are at. And again, I apologize about the video getting split, but we've had an introduction to thermodynamics and we've talked about mainly today the PV work. So we had this idea about understanding about pistons and how works can be done with the pistons. We have the gas inside the piston and we have the piston that then can be pushed down, or the gas can expand to cause the piston to go up. And this is known as the PV work, which is considered to happen under the same temperature. And so, of course, there's heating in here, but the external temperature remains the same, which is really kind of confusing because how can it be the same temperature, but there's a flame? It seems like there'd be a temperature change there. Yes, there is, but only for the gas. But the external temperature basically stays the same. And so then what's happening is the gas could expand. So here's the expansion for PV work, right? There's two possibilities. You could have an expansion or you can have a contraction. So here's the expansion version. And we talked about the system doing work on the surroundings, which we could think about as a little weight on the top of the piston, or we could think about it driving a shaft that does something like make a car go. And then on the other hand, the opposite of that is you have the contraction work where you have some weight on top of the gas and pushing that down, be it some kind of environmental or not, again, being connected to a shaft. And so then we took a look at how this might work in terms of the integral versus not doing it with the integral. And this is really a key figure that explains what's going on here. So we can see that what's really happening here is that as we integrate, we would have the minimum work that is needed to be done because we would be explaining this in terms of the infinitesimal situation versus if we did just a P delta V work, this is under constant external pressure, but we can see that the area under the graph is related, but not the same. And so that tells us about whether or not something is going to be done all in one chunk or if it's going to be done infinitesimally. And that brought us to our discussion of the state functions. So the state functions is really about whether whether something is going to be the same over the whole process or not. Does it matter on how you got there? So if it is a state function, it means that it is not dependent on how it got there. It's really just initial versus final. And that is something that is described by a delta, big capital delta. So initial minus final, the kind of stuff you do in an easy high school physics class, or middle school. That's probably what you have seen there. But in fact, there are some things that depend upon the actual path, and energy is a path independent, which means that it is not a state function. And heat is going to be another one, which is going to lead us into our discussion of the first law of thermodynamics. So here we also saw, though, that you can plug in some equations, right? And you can actually calculate these things. So we're going to need to know how to take the integral of various things, and then we would get the answer out. So here is a work reversible. So both work and heat are going to be path dependent and require the calculation of the exact integral in order to get the answer out. And the first law of thermodynamics, which we've used to wrap this up in as a bridge to our next topic, which is really going to be really getting into the first law next time about energy as a state function, is that heat and work are really complementary to each other. And even though they each depend upon how things got there, which means we're going to have to do some calculus next time, they sum up to the same number. Well, what do I mean? They sum to the same number. They sum up to this total energy, and so it really is the initial. The du will be the initial minus the final, but how those contributions add up would not be in a path independent way. So, as you might be envisioning now, next time's discussion, which is more in depth on the first law of thermodynamics, will be investigating how the total energy is going to be made up of the individual parts, which will need to be solved using the integral calculus. All right, well then, I hope that this has shed some light for you on how thermodynamics works. Thermodynamics is a pretty big topic, and we'll have more to say about this next time. All right, thanks so much, and till we meet again, see you soon. Bye-bye.